Okay, I think I'm going to start because it's time, and I'm not sure if there was supposed to be an intro for the second day. Anyway, I'll do the intro. I'm super happy to be here with you today and start this second day. I know it's early, but the room is almost full, so that's good. Thank you for coming. So I'm Eric. I'm working for Zalando, and at Zalando Tech we do all sorts of interesting things. So please come talk to me after this presentation if you want to know more about what we're doing. But first I want to know more about you, what you are doing. So can you raise your hand if you're using one of these programming languages as your main language, the one you're using like every day? Okay, so some hands don't raise. I'm still interested. So who's using something exotic that's not here? Yes, Pi. Haskell, yes, a good one. And actually, well, it's mine as well these days. So now I'm using Haskell. And it's kind of interesting because it feels like a different language. It's not kind of mainstream language, and we'll see why it's kind of different. But I didn't start with Haskell. That did not land it on me on a blue day. I started programming for one of these things. That thing is a PABX. That's where you configure all the phones you put in a company. And that kind of machine is actually quite complex. And in order to just configure what you need to put inside the machine, you need some software. So my first project was about working on such a software. And that software was growing so large and so complicated that actually its main method was 2,000 lines long in one big C++ method. It was crazy. So my main task was to refactor it. And at the time, the best tool I had for refactoring was object orientation, was OO, was this idea that you have objects communicating together, being nicely encapsulated. And it was a fantastic tool. And I was thinking at the same time, well, actually, we could also draw diagrams around that to reduce the complexity, to understand what we're doing. So I was trying hard to maintain my code in sync with the diagrams and all, and do all this OO approach, and actually it was a success. So after 2 years, we managed to significantly, break down this big method into small pieces, find new abstractions, and this project was a success. So I was super happy because it was like my first project. I had like the best tools in my hands. I knew I could conquer the world. So I started doing my next project, and this is where the problems started. And it became worse. It became worse and worse. And my success rate went from 100% to something like 50% after a bunch of projects. And well, it's definitely not entirely a problem of technology or languages. There's also project management in all of that and how we deal with requirements and all of this. I mean, things that contribute to failure are very diverse. But I was really perplexed. As a developer, it feels really bad when you see one of your projects like never go to production, for example, or just having infinite amount of bugs. So I started wondering, okay, is there anything better? Maybe I should come back to some basics. So I started investigating other programming languages, and I found out Ruby. And oh, it was quite a discovery coming from a Java background, because now you have those nice expressions. And with just one line of code, you can say so much more. I also started reading about tests and testing and bugs and defects, and it turns out that actually the less amount of code you ship in any kind of language, the less bugs you have in general. So actually having less code, more expressive code is kind of a good thing. And since I was still working on JVM, there was Groovy at the same time, and I had kind of the same goodness at once. And I was like amazed, well, there's the new world opening up to me, not only OO, but now if I have better programming languages, I can do so much better. It was nice feeling. I just had like one issue, one big thing was really troubling to me, is I want my ties back. Coming back to a Groovy project after 6 months was horrendous. I didn't know what that thing was really doing. So I really wanted a language where I could have like the flexibility of those nice expressions that were like kind of functional, acting on collections, and some type safety. And this is where I discovered Scala, and then woof, a new world opened. Functional programming, whoa, what's this thing? Monads, I don't know, new thing. So I went on to my journey, and that led me to Haskell. And eventually, I mean, while I was going to Haskell, the world didn't stop to evolve as well, right? We had like other architectures, other languages coming up on the top of the scene, and with new features, and even Java was evolving. But arriving to Haskell, I realized that in a way, the Haskell influence was kind of everywhere. And functional programming was slowly invading all the other fields, even if I was not realizing it. So that's the story I want to tell you today, is how Haskell and functional programming is deeply influencing everything that we are doing. So what is Haskell? So this is Michael Snowman. He's a very well-known Haskell developer. This is how he presents Haskell with a bunch of characteristics. Some of those are not unique to Haskell, like, I don't know, native executables or garbage collection. But there are two maybe very important characteristics that are, it's a lazy language, meaning that when you evaluate a function, you don't start by evaluating the arguments of the function before evaluating the function. You wait until you need them. It seems like one possibility, right? If you're a language implementer, maybe you can do strict evaluation or lazy evaluation, why not? But actually, this opens up a different world of programming, different way of seeing the world. And one reason why the Haskell creators wanted the language to be lazy is that it forced them to stay pure. And pure in the sense of just programming with pure functions. And pure functions is this incredible idea that it is entirely possible to program with things that are functions, that just do some kind of computation entirely based on the input, not based on the state of a global variable somewhere or the database of the weather today, and that's what they do. And the output is only specified by what the function has access inside the input, not more. Again, not some information is not going to log to the console, it's not going to write out to some kind of log file or whatever without you knowing it. That's a pure function. And that's great. That's what Haskell people have. They've developed a whole industry, if you want, of programming with just functions, because that's a wonderful idea. But what does that mean for other languages? Do they have functions or not? So periodically, you see articles like this, blog posts rediscovering functions like, hey, this is a great thing, it's a function. We can use it in Java, it has all sorts of nice properties, like testing is amazing, refactoring is so easy, you just put it there, and it was there, and now it works again. It's like people are rediscovering how wonderful it is to program with just functions, right? And you also have some old-timers in Java saying, well, you know what, functions, we've had them forever, because in the design patterns book, there are many things that you can consider, like functions like command, action. All of those are like kind of functions in disguise. And even in the JDK, you have things like a comparator interface or callable, file filter. All of those are kind of functions, right? But, well, not really. What they are not like first-class function. Things that go really from A to B and that you can pass as a parameter anywhere you want. And this is what's needed. And it's so much needed that in Java, there was really a gap between Java and other languages, especially when you start dealing with collections. I mean, having to iterate with for loops, every time you want to map and filter, it gets really tiring after a while. So it's no surprise that those kinds of collection constructs coming from functional programming languages like Haskell are invading a language like Java, because I mean, this is so useful. And to do this, well, you need functions, because you need to be able to pass things to your map operation or to your filter operation. And of course, in Haskell, well, this is so much better. I mean, the syntax is nicer because, well, it's a language that's really designed to deal with functions from the beginning. So you have nice syntax. So programming with functions is something that's slowly invading everywhere. It's very rare to accept a language that does not have functions as first-class parameters now. And then if you look at this streaming library, you can see something like this, which is quite interesting. It says, oh, be careful, don't update share mutable state. Oh, now we have to talk about mutability. And I mean, in the language like Haskell, you learn that it's entirely possible to program with immutable data structures, and you can get very far with this. And again, it's not such old knowledge. I mean, you have articles touting, or entire presentations touting the benefits of immutability, and even in the best very old Java books on how to work with Java, you have some such advice, like classes should be immutable by default. It should be like the default. So progressively, if we follow just those advice and those new tools, we realize that we enter this world of more like the FP and Haskell mindset of using functions to create data, to transform it using maps and filters and whatever, and then to consume it, right? Which is kind of a different mindset of seeing the world as a set of objects communicating together. It's a different way of seeing the world. So now let's talk a bit about data, because data is kind of different, right? Data is not really objects. And again, the old-timers in Java can say, well, we've always had data. Well, stop about it. We had POJOs, we had DTOs, and value objects. That's just data, right? Well, not really. Those things are like classes and objects, how can I say, transformed to be used as data, but they are not really nice and easy to use data. This is why in languages like Scala, you have case classes. In Kotlin, you have data classes, and in Clojure, well, you have just lists and maps, and because everything can be shoved into the same data structure, it's okay. But data is so useful as a concept inside your language that now it's also coming to Java. So there's a recent proposal of introducing data classes into Java as well. So I think this is called now records, because it's very, very useful to be able to create small data types, just holding the small amount of data you need, and then have functions operate on top of that, and that thing being immutable and all. And more, like 2 weeks ago, oh, why not I add a bit of laziness into the mix? Because laziness, after all, that thing is also useful, right? You can defer the computation of some expensive thing and then cache it, and well, that's nice. Maybe we should add a bit of that. So, as you can see, Java is also being influenced a lot by what's going on in Scala, which is itself, you can say, influenced a lot by what's going on in Haskell. And I would say that, again, I think that for describing data, Haskell is also very nice, because you have like just a nice syntax to describe all your cases, and even compared to something like Scala, the syntax is, I think, more pleasant. But once you have data, you can do so much more. So this is a blog post by Steve Yeager, when he was still at Amazon, and he described the challenge that they had internally about doing some kind of computation, solving a problem, a farmer puzzle. And he said, oh, those Haskell guys, they came up with a crazy thing. In just one line of code, they extracted just the relevant pieces in the list of sublists, where they just had to take the second element of each sublist. And that was just easy, and then they can use these elements in a complex condition. And that's pattern matching. So that's the first time I encountered pattern matching. I thought, wow, that looks interesting. And then I realized that Scala was supporting it. So that was one big plus for me, that Scala was supporting it. I could use it. But that thing is actually so useful that it's coming to every language, because once you have data, you want pattern matching. So you have pattern matching coming up in Swift, coming up in C#, and coming up in Java, because that's a very obvious complement to having data classes. It's very hard not to have it. It's also not an easy problem. I mean, in Scala, we've had bugs and bugs and bugs, and probably still more bugs for doing pattern matching properly. Even in Haskell, it's not until like GHC 8 that pattern matching was really supported properly in some of the cases that were kind of complex. So it's not an easy thing to support, but that's still something that's super useful. So I think that what this tells us is that we have a pretty different way of seeing the world now. So this is how I've been taught object-oriented. Like, you have some inner hidden state that is well encapsulated by a set of methods. Possibly those methods can change their behavior based on what's in the current state, and things happen. But now we have like functions on one side, data on the other side, and this data is not maybe so well encapsulated because you can kind of extract it, see what's inside. So it's like tearing objects apart. It's a way of seeing the world that's moving away from OO, right? So we have OO languages, but we started using them as something that's kind of different from what was the original intention of doing OO. And I think there's a good reason for this, is that this object here is like a small state machine, if it is mutable and can change its behavior based on its state. And programming with state machines becomes hard very fast, because if you put lots of those state machines together, you get like explosion of states. And this makes our systems very hard to debug, very hard to understand, very hard to reason about. So I think that's one reason why we are moving away from OO, and we are heavily influenced by functional programming and Haskell, showing that it is possible to program without OO. There's also another area where objects were like kings for a long time, like that was UIs. So for a long time, we thought that objects were like the best thing to describe UIs, describe widgets, talking together, cooperating to achieve some kind of behavior in the UI. And then those people from Haskell came up with some crazy concepts like, oh, maybe we can just model things like behavior and signals and events and have some operators based on that. And soon they were showing that it's possible to build entire UIs based on just functional concepts and combinators. And that was like kind of amazing, right? Something where we thought that OO would be king forever. So is this the end of OO? Well, I don't think so. I mean, we have such inertia in everything we're doing, so it might take like one generation. I mean, there are still thriving COBOL projects to this day, so it's going to stay for a while. But I think the influence of functional programming is very, very strong. And it's teaching us to use smart functions on dumb data, which is a different way of seeing the world. So that's one thing that Haskell is bringing to the table. It's also bringing another thing which is quite important. It is types. And before talking about crazy types that Haskell is bringing to the table, let's talk about simple things. So when you have just data and types and type checking, you can do some simple stuff that's already very, very helpful. You can start by making sure that you don't have bugs in your programs just because it's impossible to construct a faulty program. Can we try to do this? And it turns out that not in all the cases, but in many cases, it's possible. So if you say, I know that my list of products must never be empty, you can create a type representing this. It's never going to be empty. And this non-empty data type has at least one A element in it, and possibly a list of other A's. But in order to build a value of that type, you need to provide at least one A. And that's really cool because you know then that you can always take an element from this data structure. There's no risk, no exception. And with this, you can build on this idea. And there's actually, I did a full presentation a few years ago showing how it was possible to encode a process where I was synchronizing data between S3, some Hadoop clusters, some EC2 clusters, where the notion of location and what could be executed sometimes had some meaning, sometimes didn't have any meaning. And like you cannot execute any computation on S3, for example. And having some specialized data classes representing all the steps of my process and having pattern matching made me give me some assurance that I was dealing with all the cases all the time. And when I was progressing to the next step, I was in the proper situation. I could not be in a situation that was not really functional. So with just types and just data classes, you can go a long way. That's really good, right? But we can do more. So raise your hand if you know who this guy is. Okay, so for the people not raising their hand, maybe you know him better because he has a secret identity. So he's a super Lambda man. So this is Philip Wadler. And Philip Wadler is one of the original creators of Haskell. And he's brought tremendous... he has tremendous influence over many other programming languages, and Java is one of them. When Philip learned that Java had no generics, he was pissed off. He said, what? It is not possible. I mean, in Haskell, a collection, you know what elements you put in your collection. We cannot let this happen in Java. This is outrageous. We should do something about it. So he set out with other people to do something about it, and this is how we got generics in Java. And it turns out that this is actually not such an easy problem because you have subtyping in Java, something that you don't have in Haskell. So you have to take care of some of the cases that are not so easy, and eventually you come up with this kind of diagram explaining, oh, what is contravariance, what is covariance, and because there is a list of apples, is it still a list of fruit or not? This is kind of complex, right? So generics in Java were not so obvious because of subtyping. And I spoiled the next slide, but subtyping is hard. That's what we learn. And that's also part of my message today, is that we take subtyping for granted when we program with OO languages because it's a very convenient thing. Like A is a type of B, and then let's go on with it and replace everywhere we have a B, we can use an A, and that's fine. But actually, subtyping in languages creates all sorts of issues. So generics is one problem, but we have other problems. Like one thing that's coming up to Java is a better type inference. And again, when you have languages like Haskell, where all the types and many types can be inferred, And so yeah, you don't have to type that much to tell the compiler what it actually should know already. You want this kind of thing in Java to make it less verbose. So you had the diamond operator in Java, and now you have things like Project Ember, where you have this var keyword coming up in Java, again, in an effort to reduce the boilerplate. But it turns out that type inference and subtyping, they don't match really well. It's actually quite hard to do proper type inference with subtyping. And if you want to convince yourself of this, I mean, the latest advance on the subject is this thesis from Stephen Dolan, where he might have found a solution, like last year. It's like super recent, on how to do some form of subtyping and have good type inference. This is not an easy problem. So subtyping looks like a great feature, but comes with some costs. And what Haskell is teaching us is that, well, actually, maybe you don't need subtyping. It's possible to program without subtyping. And that's really cool. And one way to program without subtyping is to use another thing that Haskell is bringing us, is abstraction. So now you see, again, blog posts like this, like, oh, monoids for Java developers. What is a monoid? And I mean, for many people, I suspect that most of you here have an idea of what a monoid is, but many people, this is like really new. What is that thing? And even worse, monad. What is a monad? And what's wrong with Java with monads? I didn't know Java had monads. Well, it has, because some people were crazy enough to try to implement monads in Java using all sorts of libraries and crazy tricks. And if you turn to Scala, you have all those concepts right away. You even have like 2 libraries to support those concepts, because one was not good enough. And now we also have them in Kotlin, right? So you have a full functional programming library exposing all those abstractions that are directly coming from Haskell. So, I mean, why are they coming from Haskell? Because they are so damn useful. So you had like presentations yesterday showing you why those abstractions were so important and so useful. And one concept that Haskell is bringing to the rest of the world, which I think deserves its own space, its own representation, is the concept of a type class. So when you come from object orientation, type class feels a bit weird as a name, because you know classes, but what is a type class? So it's a way to classify types, to say that some types have some properties. And one simple example is, again, this monoid example of things that you can bash together with an append method. You can group them together, and there's also an empty element, where if you bash it with anything else, you return the original value. And so int has a monoid instance with 0 as the empty element and plus, but string has also a monoid instance, or list of anything has a monoid instance as well. And based on this abstraction, you can program more things. So you can sum all the elements in a collection without ever knowing what they really are, as long as they have a monoid instance. So that makes your program very robust, and that function is not likely to change in the next morning because you have a new type. No, that thing is super stable. It can be reused in many ways, in many places. So you learn one concept once, you learn a weird name like monoid, but then you discover, wow, all sorts of applications. And then that draws you to more scary things, like higher candy types. What is that thing? And actually, it's something that Haskell makes you realize how important it is to talk about those higher candy types. So if you have a list of A's, an option of A, a future of A, either of A, they are more or less, all of those look like M of A, right? For some M, which is list, future, option. And it turns out that they all support an operation which is flatMap, or slow, right? And this operation can be reused in many different contexts. It's really cool. Failing to recognize this abstraction has a huge price. It has some prices like this, like in JavaScript. They don't know what they're talking about, so they need to rename flatten into smoosh, because otherwise everything else is going to break. And in Swift, they had different flatMap operation for different monadic types, like sequence and optional, and now everything is breaking again, right? So abstractions are not just for the sake of abstractions. If you fail to recognize them and implement them properly, you will really fail. It's not helping you at the end of the day. And if you want to support this kind of abstraction in your language, being able to describe this thing, this is where you need higher candidate types. So this is where Haskell is showing you that having a more elaborate type system is actually super useful. Because you need to be able to talk about this A and say, sorry, this slide, to say this M has some properties, right? And you need this support inside your language. And this is how you see that people wanting to implement functional programming in Kotlin, well, they have to import this concept coming from Haskell. It has to be supported in Kotlin in order to be able to have type classes representing monads, right? It's really useful. And it turns out that actually, did you know you could also do this in Java? That's really crazy. What? Look at that. You can use annotation preprocessors and write some Java code that's has some hierarchy types. I don't even know how to read this, but it looks really cool. So what Haskell is showing us is that there are lots and lots of very interesting types. So we know about subtyping, sure, coming from OO. We know about generic types, except if you're a Go programmer and you want to have fun by re-implementing it yourself with some strange macro. Now we want to know about hierarchy types, but there are more. So if you study Haskell, you will realize that there are rank n types. And at first you say, why would I ever need this? And one day you start programming and you think, oh shit, what is that type here? And someone tells you on the mailing list, well, it's a rank n type. You need a rank 2 type. Oh, really? Okay, actually, so that's useful, right? So knowing those types change your life. Same thing for existential types. Existential types are a very nice way to actually hide information. So you know there's something, you have a name for it, but you don't know what it is precisely. And that's a very nice way of building systems. And then it opens up the whole world of dependent types, right? And you can use something like IDES, which is a Haskell-like language, or Pi, to use dependent types. So what Haskell is teaching us here is that there are all sorts of useful type system features that we can use in mainstream languages that are going to bring all sorts of goodness to our daily life. The other thing where Haskell has, I think, a huge influence, and we don't notice it almost at all, is libraries. So in a way, we notice it because we have now those nice functional programming libraries in Scala, so we have all those concepts and all. But there are more nice and interesting libraries in Haskell that are not necessarily well-known. So you have lenses. So as soon as you have immutable data that starts being nested, lenses is almost a requisite, something you need to have. Because when you want to modify something that's deeply nested, it's nice to have something like the lenses library to just say, give a path to your data structure and say, I want to modify this. And things will still stay immutable. There's no need for mutation in all of that. So this is what lenses brings you. That's really cool. That's also very mind-boggling. I mean, there are different ways of implementing lenses, and just by studying them, you will learn a lot about functional programming. Haskell pioneered QUICKCHECK. So QUICKCHECK is a very nice way to test your program by just generating more data. Describing some arbitrary generators, combining them, and expanding the amount of domain that you explored in your tests. And that can reveal some bugs. I mean, I had personally reproduced with Scala check a bug that was occurring after 30,000 tests, right? But now I was able to reproduce it deterministically. I knew exactly then what was going on. So that's really invaluable. I also really encourage you to have a look at all the streaming libraries in Haskell. There are like 4 or 5 libraries with different trade-offs, but they are all very, very, very interesting from a functional programming point of view. I don't know, my favorite of the moment is the one called streaming, simply streaming. It's really beautiful. And then you have things like ASYNC and software transactional memory for doing concurrency. So I have never been very confident as a Java or Scala programmer in doing concurrency. I was always thinking I would mess up these threads that I should awake and sleep and join and block and whatever, and I was never confident with doing any of this. For the first time, I feel in Haskell I have the right tools to do it. I have the tools where I can think, okay, I know what I'm doing. And those are really nice libraries. But I also don't want to end this presentation by giving you the impression that Haskell is bringing all the goodies and has nothing to learn from the rest of the world because it's so good and so perfect, because it's not the case. One thing that I'm sorely missing from Haskell is a module system, a way to declare a bunch of operations as being an interface to something and hide the implementation and have the ability to nicely switch the implementation with something else. I feel that when you try to build large software and you want to make it modular, you want to have some sort of components that you can reuse, that are nicely defined, that mark the limit of some domain, and so on and so forth. And you don't really have this in Haskell, so probably Haskell to take some inspiration from something like OCaml, for example, and have a module system inside. Haskell had some issues with latency. So there's a famous blog post explaining why a company could not implement their system because of some latency issues, and then they finally choose Go, which is actually quite funny because Go is very good at latency in terms of garbage collection, but at the expense of everything else. So throughput and memory consumption is very bad, but latency is good. But well, if that worked for them, that's good. But what that also means is that there's more room for Haskell to improve on this subject, on how to, I mean, let us create some caches for data that are not going to be garbage collected every 2 seconds and things like that. Another thing which is really annoying when you start as a programmer, writing your first programs in Haskell, is records. So records are just data types where you name the fields, you give some names to the fields, and those names are actually functions, so they go to your global namespace, and if you have 2 records with the same names, they just clash. So there are many different libraries and solutions to this problem, but they feel super heavy, and you feel that something should be baked into the language so that you should be able to easily just namespace those functions without having to resort to any type trickery or crazy tricks to just use your records easily. And the last thing maybe is IDEs. So when you work with Haskell, it still feels that if you want to have like code completion and linting and just compiling and testing and all of that grouped into the same tool, it takes a lot of effort. And it's likely to break in 2 months because something has changed and something is not on the path anymore, and you don't know what. So this is quite annoying. This is a price I'm willing to pay to get a better language, but I must say that this is quite annoying. For example, I'm crashing VS Code every 2 days now. I have no idea why, but that happens. Good thing it restarts very fast. So, okay, so to sum up, I think Haskell is bringing a lot to all the mainstream programming languages without us necessarily realizing it. So it teaches us that we can program with functions, that immutable data structures are good, that we don't need objects and subtyping to create nice programs, having nice abstraction and lots of reusability. And types can give us a lot more assurances in our program and a lot more reliability. So my question to you is, why not? Right? And that's it.